Here we're going to talk about electron withdrawing and electron donating groups. And specifically what we're thinking about is if we have some molecule and some atom A in the molecule, atom A is our focus, and what we want to think about is how does a group attached to A influence that group? Is it donating electrons to A or withdrawing electrons from A? So just to put this in perspective in an actual molecule, let's say we have this. What we're interested in might be this particular carbon, that's atom A, and then our group would be the Nitro Group, and thinking about how it affects atom A. So for the group, here's the question we're asking. Does this atom or functional group donate electrons or withdraw electrons from atom A in the molecule? And what we're going to do is look at a few different classes, and this is going to be useful when we talk about the Diels-Alder reaction next, but also when we begin our discussion of reactions of aromatic rings, because these groups that are attached will influence the reactivity of aromatic rings. So we're going to classify these into two groups, donating groups and withdrawing groups. In terms of our donating groups, some groups are quite strong at donating. So let's look at those first. And these strong donating groups might come as a bit of a surprise, because the strongest donating groups on an atom tend to be what we call as Z with a lone pair, or Z could be oxygen, nitrogen, or sulfur with a lone pair. And why this is potentially surprising is you might think of something like oxygen as electronegative and electron withdrawing. And because of its electronegativity, it will have some withdrawing character on atom A. But the fact that it has a lone pair is going to make it resonance donating, and that outweighs any withdrawing character. So let's look at an example of this. Okay, so in this molecule, here's atom A that we're interested in. The oxygen has a lone pair. In fact, it has two lone pairs. And what that lone pair can do is push electrons toward atom A through resonance. So this donation of resonance is donating electrons to that atom, making oxygen, nitrogen, and sulfur all fairly strong donating groups. We also have some weaker donating groups, the most common here being a simple alkyl group. So what happens in this case, let's draw an example. Let's say we have a simple methyl group as our alkyl group. So it's a subtle effect, but what this alkyl group is going to do is inductively donate electrons. And there's inductive donation to atom A. Here, this is primarily a hybridization effect. So effectively, the sp2 carbon is more electronegative than the sp3 carbon, and for that reason, electrons get pulled in this direction. So this is a slight donating group. We can also look at withdrawing groups. So in terms of withdrawing character, the most withdrawing thing you could have near atom A would be a positive charge, because that wants electrons, that's going to pull electrons towards itself. So think of this in terms of a positive charge or an electron withdrawing group. So we're going to break these down into three classes: strong, moderate, and weak. Let's look at strong first. Two of the strongest withdrawing groups are the Nitro Group and the Cyano Group. And this is perhaps easier to see if we were to draw out the full group. So let's take atom A. The Nitro Group has a nitrogen double bonded to one oxygen, single bonded to a second oxygen, and a positive charge on the nitrogen. So that positive charge on the nitrogen is pulling electrons towards itself, away from atom A. Likewise, if we draw out the Cyano group, it's C triple bond N, and the Cyano group is pulling electrons toward the nitrogen. So there's a partial positive on the carbon, partial negative on the nitrogen, and then that positive charge on the carbon is pulling electrons away from atom A. Next, let's look at a moderate electron withdrawing group. Here, the most common is a carbonyl group attached to the atom. So carbonyls are electron withdrawing, and the best way to think about this is if we draw a second resonance structure here, and we move these electrons to the oxygen through resonance, let's see what we get. What we find is the resonance structure puts a positive charge next to A. So again, that's pulling electrons towards itself. Just like that. So because of that, the carbonyl is withdrawing electrons from A, so it's a withdrawing group. And then finally, the weak withdrawing groups. These are the halogens. So despite thinking of halogens as being, electronegative and things like that, they're not super strong withdrawers. So if we have a halogen, like Cl for example, what that's going to do is pull electrons towards itself inductively. And because of that, you're pulling electrons away from A, making that a withdrawing group. This is something we're going to explore further later on in the course, but this gives you a basic understanding of donating and withdrawing groups.